Hello everyone, this is Shadowman and this is an update video on my newest Knex project, which is an 8-bit mechanical computer. And right now this video will cover the arithmetic logic unit, or the ALU. So what do I mean by an 8-bit computer? Well, this will work with numbers ranging from 0 to 255, because those numbers we can store in 8 bits of binary data. Each bit is either a 0 or a 1, so everything is stored as binary, and the arithmetic logic unit also operates on those binary values. This is a very simple ALU. All it does is take two input numbers and has an output, and the main thing that it will do is add two numbers, and I will cover other functions like subtract later on. Since the ALU operates on two numbers, we need to store those before anything is done, and that is done in these two registers back here. It's probably a little bit difficult to tell exactly how they're stored. I'm going to cover the registers in a later episode when I talk about data transfer, because I don't have that part finished yet. So for now, all you need to know is 1 bit is stored like so. When I pull this out, that stores a 1, and having it pushed in, that counts as a 0. You can see that blue rod going left and right. When it's over the green connector, that's a 1. The first register is here. I'll just call that the A register, and it has 8 bits going all the way down. Also, you might have noticed there's actually a third register, and I call this the sum register, and this is where the number is stored after the ALU gets an output. It will put it out to here. It looks just like all the other ones, and you can see that right there, and I'll cover more of that in a little bit. The way the ALU adds two numbers column to column is pretty much just like what we all learned in elementary school, where you start with the first column, you get your first digit as the sum, and if there's a second digit, that just goes as a carry to the next column. Here I'm showing the first bit that will be added, and for the B register, you can see in here that green rod is a pin that slides back and forth. Same with the A register. Each column has this sliding assembly that starts at the bottom and goes up the gray rods, and this is actually a counter to count those bits back there. So each pin, it will increment 45 degrees. It might be easier to see from below, so that those orange connectors coming down, that's the sum pin, and this here is the carry pin. So I can just slide this up, and if it counts 0, nothing happens. This is 1, so it lifts that up. This is 2, so it activates the carry pin and does nothing to the sum pin. And then a 3 will push them both up. And the way the sequence goes, I can't really do this by hand, but it will count it right there at the correct time and release it, and also activate the sum pin. This is what it looks like when all of the bits, including the carry in bit, are all set at 1. So this is going to output a 3. So you can see that counter incrementing. And when it goes all the way up, the sum bit just went to 1. And the carry bit is activated, so that it got sent over to the next column. Before I explain how the drive system works underneath, let's actually see it working. The way this works is pretty simple. It just has a chain, and these pins on the top are going that way. The motor is on the other side, and it pretty much acts like a rack and pinion. So they'll go back like that, and there are 8 wheels right there going all the way down, and those each hook up to a crank, And there's enough pins on this chain to make this crank go around 360 degrees. And they just connect to the big yellow gear. And these weights right here keep the cranks in an exact position. That way these counters always stay at the bottom. And of course there's a counterweight back here so that this whole process doesn't use up that much force. Also, it looks pretty cool when viewing everything from this angle. The reason it paused and you heard some popping sounds is I actually have a new type of transmission to power this, and it has a safety mechanism, and I just have to adjust it a little bit because right now it's a little bit too sensitive. So here's where the chain is actually powered. You can see this is the last column right here. So this moves pretty fast, but right now it doesn't do anything. And to turn it on, I can just push this. So now it's engaged. And those yellow connectors stop it, and there it is. And now it's off. So you saw it kind of pop. When it pops, it goes around again and tries again, and it does that until it stops. And let's see if I can get there's a spring in here that can be adjusted so that it doesn't do that popping so often. No wonder it's been disengaging so much, because this spring right here isn't even attached on one side. So it's this orange connector and those two blue rods will spread apart. And right now it isn't even attached to anything. When the lever is pushed to turn it on, you'll see that that goes down. You force it this way, and then it can do that in order to engage the safety. All this other stuff that you can see above the chain is for a later episode. I'm almost finished with it, but not quite. It looks like a mess, but I promise it's just organized chaos. And for the ALU to turn itself off, when the chain comes to this point, it'll push those green connectors up that are on a lever, and it will push that. And this is a spring-loaded switch, and this part right here enables this to be turned on. So we could add two numbers, which is cool, but there's got to be more that we can do with this thing. One thing we can do is make a binary number negative by representing it in its 2's complement form, and I'm not going to explain the math behind that or how it works. There are several videos you can look up that explain it. Basically, if we make a binary number 2's complement, it's going to use the most significant bit, that's the highest bit, the one over here. It's going to make that a 1. And no matter what all the other bits are, if this bit here is a 1, then that means that number is negative. In order to make a number negative, we have to load it into the B register, and then we need to flip all the bits, so we do a bitwise invert, and then add a 1. So we can do that pretty easily with this carry in right here, which isn't really attached to anything yet. So setting that in like that will be done in subtract mode. And also this will be set, which inverts all those bits for the B register. Doing that with a carry in of 1 will be the same thing as doing A minus B instead of A plus B. I can show the bit invert better from this side, so you can see that bottom pin to the B register is set at 0 right now. Let's get it in focus. Right now it's 0, right now it's 1, but you can see that other one on the orange connector. If I flip it, now all of a sudden, instead of being 0, it's a 1. And when I make it 1, it misaligns it with the counting wheel, so now it's a 0. So that essentially inverts all the bits that are in the B register just by flipping this 90 degrees, and that is connected all the way down. But we aren't even stopping at just adding and subtracting, because that's just the arithmetic part. We also need some logic operations to make it a true ALU. So we already have bitwise invert with the B register if we just flip that 90 degrees, and we have an increment, which is pushing that in. But we also have AND mode, which instead of those two numbers being added, they'll do bitwise AND. So if both bits are 1s, it'll output a 1 at the sum register, and if any of them are 0, it'll just output 0. To do that, all we need to do is manipulate where these counters start. So I have an AND mode lever back here, and now they start at one position backwards, so now it requires 2 1s on this column in order for this to get to that position, and then push the sum bit. And the carry bit doesn't apply here, so it will only ever get to this point and not hit any carry pins. One other cool thing is that we can actually have a decrement, because -1 in binary is all 1s. So all we need to do is make sure the B register is set to 0, and then we can modify the AND lever to go the other way to set them all initially at this position. This will cause each column to automatically count the B register as a 1, and then whatever is in the A register will be added onto that. And of course, since it's -1, it's actually whatever's in the A register minus 1. We can even do bitwise XOR or exclusive OR, which means that the output is 1 if there's a 1 and a 0 being operated on. But if they're both 1, then the sum pin should be 0. And that's basically just what happens. If any of them are 1, it does that, and that hits the sum pin to be 1. And if it counts 2, then it'll do nothing. But the main thing we gotta remember to do is apply that wave motion in reverse. That way all of the carry pins will be ignored. Otherwise, it would just do a normal add operation. One last and very important thing that the ALU needs to have are flags, so that we can do conditional branching later on, which will be able to skip to different places in the program, depending on what result was calculated. To do that, we have 3 flags. We have a 0 flag, a negative flag, and also an overflow. All of these flags are actually pretty simple to implement. We have this bar up here, and if any of these sum bits is a 1, it'll make it be up like this. If they're all 0, it'll be down, and this also doubles as something that will be used to reset all the sum bits. To do a negative flag, that's also pretty easy, because like I said earlier, we just gotta check this first bit if it's a 1 or 0. So if this is up like that, then the negative flag will go off. And for the overflow flag, that is this special carry bit right here, which isn't attached to anything yet. This happens if you try to add, say, 250 plus 10. The result in the ALU will be incorrect, but it will push this carry pin up, letting the program know that there is an overflow. That's pretty much it for this video. That explains most of the ALU and all of its functions and all the operations that we'll be able to do. In the next video, I will have the data transfer finished. Right now, I only have really half of it, even though it's taking up this whole side here. When the next video comes out, I will start having the RAM stack, which will be directly above the registers. Hopefully that was a good enough explanation of how all this works. Thanks for watching, and I will see you in the next video.